Here's a fact that should reframe everything you think about modern farming. The United States spends roughly 40 billion a year on synthetic fertilizers. Farmers apply nitrogen, phosphorus, and potassium to their fields in carefully calculated doses. And then some portion of that investment, at least on some fields, a very large portion of that investment simply just does not work. Not because the fertilizer is bad and not because the application was wrong, but because the soil won't release the nutrients to the plant. The fertilizer is there. The crop just can't access it. The single variable that controls whether that 40 billion delivers a return is a number most people outside of agriculture have never really heard of. It's soil pH. This is Agri Written. I'm Vincent Seal. Every Thursday, we do one of two things. We take something fundamental to agriculture and explain it from scratch, or we profile one of the companies that shape it. Today, soil pH, and why it matters more than most people realize. Soil pH is a measure of hydrogen ion concentration in the soil solution. That thin film of water that coats soil particles and that plant roots actually drink from. The pH scale runs from 0 to 14. 7 is neutral, like pure water. Below 7 is acidic, and above 7 is alkaline. Most agronomic crops, such as corn, soybeans, and wheat, perform best somewhere between 6 and 6.8. Now that may sound simple, but here's where it stops being simple. The pH scale is logarithmic. It's not linear. That means each single unit on the scale represents a 10-fold change in hydrogen ion concentrations, not a 10% change. A soil at a pH of 5 is not slightly more acidic than a soil at a pH of 6. It is 10 times more acidic. A soil at pH of 5 is 100 times more acidic than a soil at a pH of 7. When a farmer's soil test comes back at 5.5 instead of 6.5, that field is not a little low. The hydrogen ion concentration is 10 times higher than optimal. That distinction changes the scale of the problem entirely. What pH actually does is control whether nutrients already present in the soil are chemically available to the plant's roots. This is the thing that earns approximately 10 minutes. A farmer can apply full fertilizer rates and still starve their crop, because those nutrients are locked in a chemical form that the plant cannot access. The phosphorus is there in the soil, but the soil pH is wrong. Therefore, the plant goes without it. Soil pH is not a fixed property assigned by geography, but geography does establish the baseline condition that determines how hard that management problem is actually going to be. The core driver of natural soil acidity is rainfall. Rainwater is actually slightly acidic, around a pH of 5.7, because atmospheric carbon dioxide dissolves into it and forms carbonic acid. As that water moves through soil, it leaches out calcium, magnesium, and potassium, the base cations that buffer acidity, and leaves hydrogen and aluminum behind. High rainfall regions lose base cations faster than low rainfall regions accumulate them. The result, the eastern United States, the upper Midwest, the Pacific Northwest, and the humid Southeast all have naturally acidic to moderately acidic soils. Much of Georgia, Alabama, and the Carolinas sit at baseline pH values between 5 and 5.8 before any agriculture intervention. The Great Plains and the arid West run the opposite problem. Low rainfall means those base cations aren't leached. Calcium carbonate actually accumulates in the soil profile, and the pH sits between 7.5 and 8.5 and sometimes higher. The agricultural challenge there is alkalinity, a different set of nutrient lockouts, particularly for iron, zinc, and manganese. Agriculture also accelerates acidification everywhere. The dominant human driver is ammonium-based nitrogen fertilizer. When ammonium, NH4+, the positively charged form of nitrogen, converts to nitrate through a microbial process called nitrification. It releases hydrogen ions into the soil solution. Every cycle of that conversion pushes the pH down. Corn-soybean rotations in the Corn Belt under standard nitrogen management acidify surface soils at roughly 0.1 pH units per year, according to Iowa State University research. Across a decade without liming, without applying the calcium carbonate that neutralizes acidity, that is a full pH unit of decline, from 6.5 to 5.5, a tenfold increase in acidity, compounded slightly across millions of acres. No one company controls soil pH itself. It is a chemical condition distributed across every farm field on Earth. What companies control is the primary remedy: agricultural lime, crushed limestone, calcium carbonate, that neutralizes soil acidity when applied to fields. The global agriculture lime market was worth approximately $3.8 billion in 2025. The dominant producers are a handful of large industrial quarrying companies like Elhoist, headquartered in Belgium, operating in more than 25 countries. Carmeuse, also Belgian, with major North American operations. Graymont, based in Canada and dominant across North America and Asia Pacific. Martin Marietta Materials, which has assembled a quarry network across the Eastern Corn Belt and Southeast, and United States Lime and Minerals, known as USLM, publicly traded on the NYSE. Here is the structural reality that shapes all of this. Despite the presence of large players, the top 5 global producers collectively hold only 28 to 33% of global ag lime revenue. The rest is distributed across hundreds of regional and local quarry operators. The reason is economics. Agriculture lime is a low-value, high-weight commodity. A ton of ag lime is worth $20 to $70 at a quarry. Shipping it 100 miles can cost as much as the material itself. So the market is intensely local. A corn farmer in southern Indiana buys from whichever quarry is within 30 to 50 miles. A farmer in rural Georgia has a completely different set of options and a completely different price exposure than a farmer in central Iowa. This geographic constraint creates an access problem that is easy to miss from the outside. In regions where limestone deposits are absent or sparse, parts of the Pacific Northwest, areas of the Deep South, much of sub-Saharan Africa, the cost of lime correction rises sharply or becomes economically prohibitive. The soil stays acidic, not because the farmer doesn't know it needs correction, but because the correction is too expensive to deliver. The USDA's Natural Resource Conservation Service runs programs to subsidize liming in underserved areas, but coverage is uneven and demand consistently exceeds available funding. The economics of soil pH management are defined by a striking asymmetry. The cost of the input is low. The cost of ignoring it is substantial. Agriculture lime runs $20 to $70 per ton at the quarry. Before transport and spreading, a typical corrective application for a Corn Belt field that has drifted from pH 6.5 to 5.5 requires 2 to 4 tons per acre. Add delivery and spreading, and an all-in cost of $50 to $200 per acre is realistic, depending on distance from the quarry. Maintenance applications after the initial correction are smaller, roughly 0.5 to 1.5 tons per acre every 3 to 5 years. The return on that investment is well documented. Corn yields on pH-corrected soils versus comparable uncorrected acidic soils improve 5 to 15% depending on how severe the pH deficit was. At 450 per bushel and 180 bushels per acre, average Corn Belt yields a 10% improvement is 18 bushels, or $81 per acre per year. Against the corrective lime application that amortizes over 4 to 5 years, the math is favorable. The North American ag lime market was approximately $1.3 billion in 2025. The US alone consumes roughly 26 million metric tons of agriculture lime annually, the largest national consumption in the world. The number reflects how much active soil acidification management the US row crop system requires simply to maintain yield potential under intensive nitrogen use. The global market is projected to reach 6.1 billion by 2034, growing at roughly 5.4% per year. That growth is driven primarily by Asia and South America, where soil acidification from intensive nitrogen use is accelerating and lime application infrastructure is less developed than in North America. Brazil, where acidic soils cover nearly 70% of arable land, is the single largest growth opportunity in the global lime market. The primary threat is not dramatic. It is quiet, cumulative, and already underway at scale. Progressive soil acidification is outpacing liming investment across large parts of the global agricultural system. The mechanism is consistent. Nitrogen fertilizer applications push soil pH down at roughly 0.1 units per year under intensive row crop management. And farmers test soil every 4 years on average, sometimes less frequently when commodity prices are low and input costs are high. By the time a soil test triggers a lime recommendation, the field may already be at a pH of 5.8 or lower. At that point, correcting back to pH of 6.5 requires 3 to 4 tons per acre. And lime typically takes about 12 to 18 months to fully neutralize acidity after application. By that time, multiple crop seasons of yield drag have already occurred before the problem is addressed. China is the acute case. Chinese farmland soil pH dropped an average of 0.5 units between 1990 and 2010, roughly a threefold increase in acidity across some of the most intensively farmed land on Earth in a single generation. That decline was driven by nitrogen application rates that exceeded crop uptake by 133 to 429 kilograms per hectare in some regions. The agriculture productivity losses from that acidification are not fully recoverable on short timescales because lime moves slowly through the soil profile, and subsoil acidification below the plow layer is much harder to correct than surface acidification. In the US Corn Belt, the failure mode is subtler. Fields maintained slightly too acidic to capture the full return on the fertilizer investment compounded across hundreds of millions of acres year after year, with the loss showing up not as catastrophe, but as a persistent gap between what the crop should yield and what it actually does. So why does this matter? Soil pH is the master variable that determines whether the global fertilizer system delivers on its chemical promise. The world spends approximately $200 billion annually on synthetic fertilizers. That spend is premised on a crop taking up the nutrients and converting them into yield. When pH is outside the target window, a meaningful fraction of that phosphorus investment is immediately bound by iron and aluminum in the soil and becomes unavailable. Not depleted, just locked. The fertilizer is on the books as a cost. It is not on the books as a return. Globally, approximately 50% of current arable soils have a pH at or below 5.5, below the threshold for optimal phosphorus availability for most major crops. Sub-Saharan Africa carries the most acute version of this problem: naturally acidic, deeply weathered soils, minimal lime application infrastructure, and low baseline fertilizer use. The combination creates yield gaps that cannot be closed by adding fertilizer alone. You cannot fertilize your way out of a pH problem. That is the structural implication worth carrying out all of this episode. Soil pH is not a soil chemistry technicality. It is the gate that every other agriculture input has to pass through. Get it wrong and the system loses efficiency at every level above it.